Well, good morning and welcome to lesson 5 in CE3372 Water Systems Design. I just sent a message to the group chat that asked if there was anybody out there. Nobody replied. That's kind of sad. So, are you? Yeah, they're okay. Thank you, Mitchell. Thank you, Lucy. Now I feel, Ashlyn, hopeful. Okay, good. So at least for 3 of you, 4 of you, 5 of you, 6 of you, 7, the group chat's working. Excellent. Very good. It's 10:59, so I actually feel obligated to stall for a minute or two before I go into the formal presentation. And today we have a helper. Let's see if I can make this work. Dusty the cat, who's decided to help me by staying in front of the keyboard. Yeah, go ahead and look at him. It's okay, Dusty. Say hi to everybody. Sorry. The startle's pretty easy. And all right, so it's now proper starting time. So I have the blackboard for this course. This is section 2, and today is lesson 5. And I'm taking the content module link, and this should take us to the content server, so that works correctly. This is an older style sheet, but the topic is review and application of pipeline hydraulics. So we're going to look at some more review as we're moving on. And we have the usual reading materials, which I'm checking as we talk, or as I talk at you, to be precise. There should be no video links. Those links will be populated once we have the videos. And this does have a supplemental data set, which we'll visit later on. And I think these are the same spreadsheets from last time. So let's go forward with the lesson notes. So pipeline hydraulic examples. So all this lesson is revisiting use of the energy equation in pipelines, mostly to simply refresh our skill in that. It's not a difficult lesson. And we're going to study using the online tools. So we've seen this picture before. I get a lot of mileage out of it. In this case, we're going to consider entrance and exit losses. We're told the material is concrete, and we'll just use the online tool. This would be easy enough to do by hand if we wanted to. So our first step is to determine what the roughness height is going to be of the material. So apparently there's this database that's available, and that's what's hidden in the data section. So let's go ahead and do that live, and then I'm going to see if this will let me spawn another window. Oh, cool. Okay, this is how I want to do it. So there's our lesson, and here we're going to go to the toolkit, and in the material properties databases, there's one called roughness height. And we want concrete, ordinary concrete, none of that extraordinary stuff, just ordinary. We submit it, and it says the absolute roughness in millimeters is 1 millimeter. So that's where this sheet came from. And now that we know that, we can convert millimeters into feet. We'll go back to our toolkit to do that. And one of the tools we have is unit conversion, and we want convert various units. Be nice if we could do millimeters into feet we can't, but what we can do is do feet to millimeters. So I'll make an initial guess, and 0.001 feet is 0.3 millimeters. So first we'll go up an order of magnitude. Now we have 3, and we need to go down by a third. So we'll go with that. 0.0033 in feet is 1 millimeter. Apparently 0.00328 is going to be even better. And lastly, we need to look up some water properties to find out the kinematic viscosities is important in our pipeline calculations. So we want to know that. And so we will go ahead and look up 50-degree water. That, oddly enough, is in the fluid mechanics tools. And it says our kinematic viscosity is 1.41 times 10 to the minus fifth. So these are using the online tools that are available to us from this class. So next we need to consider the minor loss coefficients. If we were to visit water distribution systems, we would find this table right here, which has the entrance of 0.5 and the exit of 1.0. This also in the NCEES supplied reference for the FE exam. It's somewhere in that, probably in the 180 pages, somewhere on page 180. I don't actually remember the manual by my memory much anymore. Or we could look at any of these other documents, and something like this exists and will be pretty close to these values. So we have an entrance value of 0.5 and an exit of 1. So now that we've collected the various pieces of information, we can use our online tool, or we could even use a Jupyter Lab notebook that we created back in Engineering 1330, which none of you have had because this is the first semester it's ever been taught. So we'll go with the online tool. And with the online tool, we have flow between reservoirs, no pump, U.S. customary units. So we're going to choose that one. And we get this picture, which is what we're looking for. And now we have to go ahead and provide the entry data. So we'll just put the upper pool at 20 feet and the lower pool at 0. So that's our 20-foot elevation change. And our pipeline length is 10,560. It's a 2-mile pipeline. Pipeline diameter, I believe, is 2 feet in this problem. I'm going to cheat and look on the head. Right. 2 feet. Sand roughness height is 0.00328. It's 1 millimeter. Kinematic viscosity is 1.41 times 10 to the minus fifth. Let's see if we can do a copy and a paste. We can, except we missed the 5. Acceleration of gravity is 32.2, which kind of seems dumb if it's an SI unit. It should know that. And now we're going to look at our fitting losses. We have an inlet loss of 0.5 and exit loss of 1. So we supply our inlet loss and our exit loss. For the time being, we'll leave the other two fitting losses as 0. But if we had bends or twists, we could add up all the loss coefficients for those and put them in these entry blocks. So what's going to happen when we submit the query is it's going to run Jane equation once, to get the initial estimate, and then it's going to refine on that to produce a flow estimate. So it's using the explicit Jane equation that we've seen last time. Submit the query, and it claims we're getting 10.21 cubic feet per second, which is pretty much the same as in the PowerPoint presentation. So that's a tool for these kinds of problems. If we did the same thing using the Jupyter Lab notebook, the same input information, we get almost the same number. And what the Jupyter Lab does not do is it did not account for entrance and exit losses. So we're going to look at a more complex problems. So the next thing to consider is, in many cases, we can link the systems. So we can break our hydraulic system up into parts, decompose it, if you will, and then analyze each part. You can't break them up into parts willy-nilly, per se, although I suppose you could. Generally, we look for air gaps in the system somewhere and use that to identify the breaks, but that's not always possible, and it's not always required. So we're going to look at an example where we're going to break a system into a few parts and make an analysis of it, and use that analysis to guide a pump selection. We haven't talked about pumps yet. That's coming up, I think, on Thursday. But this is a good segue into that lesson. So let me read the bullet points to you in case you didn't read them yourself. A hydraulic system can be analyzed as a set of linked components in order to make an otherwise complicated system easier to analyze. That's the whole point of doing it. And the idea is to break the system into independent parts, analyze the parts, and then reassemble to answer questions about the whole system. And I claim it's best illustrated by an example. So here's the example I want to use. So this is an aerial image of somewhere in Zimbabwe. This is Lake Gulameta. I can find this on Google Earth with some difficulty. I don't know what Harare is relative to this. It's a day's travel to get to this area. And so there's a reservoir that was built actually back when the British occupied this area. Later the nation became Rhodesia, and now it's Zimbabwe. This reservoir feeds into a lift station or a pump station right here, which is at elevation 965 meters. The reservoir pool elevation is 975 meters, so the reservoir is about 10 meters above this pump station. And then we want to pump water along this pipe alignment, come over this apparently dry stream bed, and comes up to a storage tank on the top of a hill. Then from that storage tank, we're going to deliver water to a smaller storage tank, which is located on a school. So the children of the school and the teachers and the families can come to that storage tank, and the purpose is to save the community members a relatively long walk to get water. And that's a quaint idea for us, but having to walk half a day to get water for your family is quite real for a large part of the population of the globe. Not so much in the United States, but in other parts of the world. And so this renewal project, this is something that Texas Tech students had a big input on a few years ago to build these additional facilities for this community. The students actually helped with some of the trenching and placing the pipeline and doing the solvent welds to glue it all together. Basically, very educated plumbers, but they got it built and it's in service today. So let's continue with the problem setup. So where the cursor is circling now is Lake Gulameta, and it's delivering into a pump, and that pump is pushing in a pipeline that's roughly 3,200 meters long. That's 3.2 kilometers of HDPE. It was laid by Texas Tech students working with the village authority here to make that first connection. And then there's a tank on the hill that's already there, left over from prior times, and the water's discharged in the top of that, and it can fill up to 6 meters. And then there's valving and control equipment to only add water to the tank when the water level goes down. Coming out of the bottom of the tank, there's some valves, and one of them is attached to a continuation of the pipeline that itself is 800 meters long. It comes to the schoolyard, goes up 3 meters, and discharges into the top of a small elevated tank. And then the small elevated tank is where the water is drawn from, and then people take it to their houses. The base elevation of the big tank on the hill is 1,000.3 meters, and hence the pool elevation when this tank is full is 1,006.3 meters. And so one of our jobs as engineers would be, what kind of pump do we need here, and what are the flow rates under normal conditions and when things go wrong? And so one of the things that can go wrong is that this float valve, because from here to here is gravity flow. From the big tank to the schoolyard tank is gravity flow. So this float valve could fail in the open position in some way, and the tank can overflow and keep overflowing. And so a reasonable question there is, what's the flow rate going to be? And that's important for questions like, how long will the big tank on the top of the hill have water in it? How quickly do we have to repair this mess? A second thing that can conceivably go wrong is this output valve can fail in the open position. Someone can draw water from it. I have this thing 6 feet in the air, more likely to be down where you can get to it, where the children can get to it. But they could leave the valve open, or the automatic spring closure on the valve could fail, and that could fail in the open position. And the question there is, again, what's the flow rate coming out of the system? How much water are we going to lose over time? And in that case, more importantly, can the pump provide enough makeup water to keep the system full of water until we get around and fix the broken valve? From a water quality public health standpoint, we want the pipes to always have water in them. And certainly in this part of Africa, I don't think that they're going to enforce a 35 psi, but we want positive pressure in the pipes so that water has to leak out. There's a lot of wouldn't tell by the picture, but there's a lot of ranching and cattle that are in this area, and we don't want cow poop getting into our drinking water, because then you get dysentery, and it's hard on the diapers. You'll be walking around in poopy diapers all the time. So there's our problem setup. So, what would a hydraulic engineer proceed with next? Well, we would give ourselves some questions to answer. Let's analyze how the system would behave when the float valve fails at the school, if the outlet valve is accidentally left open, and that's, again, to help us select a pump operation under the worst failure mode. And if the pump fails, time until the system fails. System failure being defined as it's out of water. You can't deliver any more water to the outlet valve. So we'll take the first problem. The float valve fails at the school. So we see all the system here, and at first glance it's like, well, that's a lot of pieces. But because of the way the water is delivered in this tank, technically it's air gapped. So we only have to analyze this portion of the system. Furthermore, because we're saying the float valve is failing, we don't care what the outlet valve is doing or this tank is doing. We're just going to treat the outflow up here as free outflow at whatever elevation this pipe outlet's at, which is 992 meters. So that leaves us the case where we have an upstream head of 1006.3 meters, downstream head of 992 meters. We have two bends, so there's a bend down here and a bend up at the top to bring the water into the tank. I guess there's actually three bends. The float valve itself has a pretty high loss coefficient of 70, which is looked up in a table. The upstream valve, which is where the large tank distributes into the pipeline, we're taking that as having a valve coefficient of 0.15. We have one inlet at 0.5, the two bends, and then the outlet's free to the atmosphere. We won't worry about outlet losses. We're going to get a lot of losses from the flow valve anyway. The viscosity of the water is 1 times 10 to the minus 6 meters squared per second. And the roughness height of high density polyethylene is 0.007 meters. And that we can check on our online deal. We'll be back at this worksheet in a second. Let's check the roughness height that has high density polyethylene. The closest we have, I think, is plastic pipe. And it claims 0.007. Oh, that's suspiciously the same number. I wonder if I cheated. And there's all the information we need. And so we can now create a hydraulic model. So I'll go through that. Run our flow between reservoirs, no pump in SI units. And 1006.3,992. So 1006.3, 992. Pipeline length is 3,200. 800. Yeah, it's the short side. Diameter is 0.127. Sand roughness height is 30,007. So that's sand roughness height expressed in meters. Kinematic viscosity. I think those are in the right units. Gravitational acceleration is the oh-so rare 9.8. And we'll do one pass with all the inlet losses set to 0. So this is pipeline loss only. Okay, so for pipeline loss only, we're looking at 21 liters per second would be leaving that system. That's a fair amount of water, actually. But let's go ahead and include the valve losses. So we have 0.05 inlet loss. Yeah, move your paw, dude. We put an exit loss of 70 that represents the float valve. We'll put a some fitting losses for the upstream valve 0.15, and then we'll take the two bends as 1.5 each, which adds up to 3. So that's what that 3 is. Inlet loss, exit loss at the float valve, valve loss at the upstream shutoff valve, and then the bends and the other fittings, that's its K value. Run the program, and we get 16 liters per second, which is still a fair amount of water. That's 2 8-packs of 1 liter water bottles at the store every second. They get kind of tiring if you had to carry it. All right, so this one gives us 16 liters per second. Move on to the next one. So this is the same again, just continuing the example, and it's in go slow mode. Let's look at the second case where the outlet valve is left open. Everything else is working as it's supposed to. And in this instance, the schoolyard tank can be treated as a circular tank with diameter D, and we'll just treat the outlet valve as if it was ripped out of the tank, and so there's just the hole. And we do have to look at the drawing to find out how big that hole would be, and there's no information on that. Well, I'll make something up as I go. So I have an output of 0.05 meters, which is 2 inches. We'll go take a look at that in the unit converter. Do I have inches? Oh, I don't. Well, I know that 1/10 of a foot is pretty close to an inch. So that's 0.03 meters. So I have I think I'm probably about 0.16 feet, which is probably around 2-inch diameter. Okay, so that's how big the hole is, 2-inch diameter. And we know the tank has 1 meter of water depth at least when this thing starts. And so the maximum flow rate is when the tank is full. And as this goes down, of course, the flow rate gets smaller. But we'll treat it as a hole in the tank, and we will go back and look at what the outflow is. And that's discharge, computes discharge from a circular hole in a circular tank. So, about 2 inches. Tank diameter is given as 1 meter. Tank depth is given as 1 meter. We'll go ahead and ignore any discharge coefficient losses for the time being. And we'll do it on Earth. And we get 8 liters per second. If we put a discharge coefficient about 0.6, which probably would reflect the losses going through the valve. We have 1.4 liters per second. Excuse me, 14 liters per second. So I think I'll take the worst case of that. No, it's not working right. Oh. Here's one for Bernoulli analysis. Yay, 8 liters per second. So we have about 8 liters per second in that case. So let's look at what we know so far. If the float valve fails and the system continues to stay full of water, we expect 16 liters per second to exit out of the system. If the outlet valve is left open, we expect 8 liters per second. Let's go analyze what happens if the pipe itself fails. So it's going to coincidentally be the sum of these two, but that's a coincidence. That's not a hydraulic thing. So if the pipeline itself fails, we go back to our this guy. Okay, so I think that was our prior setup. Now what changes when the pipe itself fails? Seems to me that the water would not flow through the valve, and it's not going to go through those bends. So those two losses go away. We run that, and we get 22 liters per second. So rounding up to 24, so I must have zeroed out some other things. So the pipe itself fails is 24. So let's ask ourselves now how big a pump we might need. We can determine that by looking back at the original drawing. And the pump has to take water from 975 meters and lift it to 1006.3. So our first guess might be 1006.3 minus 975. Oh, the pump has to produce 30 meters ahead at 24 liters per second, and that should handle the two failures. It's probably not the best idea to pump Lake Guatemala dry, but it'd take a long time. So let's see if we can find a pump that does that. Before I proceed, I just want to note that this isn't the whole story. So we're going to size a pump and we'll discover it won't work, and I'll show you why. So if we go looking through catalogs, we might come up with this as one of many, but this is a Kirloskar KOS number 1537, produces 28 liters per second at 30 feet ahead. It's like, well, 28 is bigger than 24, 30 is bigger than 29. That should work. Now it's designed for 100 millimeter pipe, so we'll have reducer expanders, so we can get some head losses connecting our polyethylene pipe into the pump, suction, and discharge. But it's already producing more flow and more head than we think we need. So let's first figure out the minor factors to put into the pump side of the system. So we'll get 2.55 for the reducer and 0.32 for the expander. And now let's go ahead and analyze it using a different but similar program that we already have located on our web server, and that's flow between reservoirs with a pump. SINs. So now we need to supply the elevation of Lake Guatemala. Addressing the chat box, Raju, you have one incorrect input. I'll go ahead and generate the same error to show you how to resolve it in a second. So we want to put pool elevation of 975 and 1006.3. 975. 1006.3. Pipeline length is 3,200. Pipeline diameter 0.127. Sand roughness, I think it's that guy. And now we have some fluid parameters. And I'll explain these. I'm going to go ahead and enter this worksheet incomplete. I did not specify values here or anything here, so I should get a message that looks like that. So Raju, that's what's happening to you. You have one or more incorrect input when you get the server error message. The way to verify that is to pick one of the simpler worksheets and leave it blank and enter it, and then fill it out and see that it works. So everything has to have a value. We'll go back and change these zeros to something else in a minute. Now we're going to have to add a pump performance curve. And let's see what we have to work with. So this pump produces 30 feet ahead at 28 liters per second. So that's one point on the curve we can supply. 30 meters per head at 28. We look here, Shutoff head is when the pump can't deliver any more flow. So shutoff head looks like it's probably at 38 or 40 meters. I'm going to go ahead and put 40. And I'm looking at these numbers as they get smaller and smaller. This was like a 12, a 6. So 38 is going to be 3. 40 is going to be half a 3, maybe 1.5 liters per second, maybe less. So that's essentially where shutoff is around 40. And pick one more point on the tabulation. Let's look at 20 meters at 35 liters per second. See if I'm reading that right. That looks about right. 35. And so now we'll go ahead and let it do its thing. So we've done that. We put in a pump curve from the manufacturer, and we look down here and go, whoa, hold the boat. It's only making 7 liters per second of flow. And that's because we forgot the pipeline head loss when we initially specified the pump. We actually forgot a few other things. So let's go ahead and get this complete. We need the head losses around the pump from the fittings. So 2.55 and 0.32. That takes care of those losses. And we have an inlet loss of 0.5 and outlet loss of 1. Look up from the table. Run that again. Not much change in the flow rate, but now we've got all the losses. Look at what we're asking the pump to do. It's actually having to deliver almost 40 meters of head to overcome the pipeline friction. If we go back to this, 40 meters of head is out here. It's pretty much close to shutoff. So now we have a problem. So we can only produce 7 liters per second because of the pipe friction. So we have to make a choice. One is to go look for another pump. That's probably the smartest choice, but why take the smartest choice when I can look at some other one? A second one that's worth examining, even though you may never buy it and build it, what would 2 pumps in series do? If you recall, and you'll relearn next time again, 2 pumps in series can add head. At the same flow rate, they add head. So all the heads double if we put 2 in series. So we're going to put 2 pumps in series, so that 40 becomes an 80. That 30 becomes a 60. That 20 becomes a 40. Nothing else changes. So now we have 2 pumps pushing into each other, and we get 17 liters per second. Recall our goal is 24. So I would argue that this sort of works with 2 in series, because we're probably not going to need 17 liters a second very often. But for grins, let's just go up to 3. So here's 3 pumps in series. And we get 22 liters per second, 3 pumps in series. Now, we'd never specify 3 of these pumps in series. That's stupid. We'd look for a bigger pump. 2 in series you might actually do, because there's some other advantages you can leverage from that. So 2 in series almost work. 3 in series we get here, and the advice would be to search for a larger pump. And that's the example of linking systems and using the hydraulic calculators that we have. Trying to think, we should probably take a look at the script that does this, but I've got to remember how to do that. So are there questions? I'm going to go ahead and access the server so you can see the actual calculations that were happening behind the scenes. Usually I don't do this, but going awful fast today, so I wanted to Okay, first we're going to look, so when we activated that online thing, here's what it went to. We entered the data into that HTML sheet, into the form. And what the computer on the back end did was ran this script, which was, it got the H1 value, the inlet value, the shutdown value, the H2 value, outlet value, and so on, all the values that we entered in the form. So if you leave any of these blank, when you go ahead and run it, you get the server error. Then it's building an input file to run a script. We're going to go look at this script in a second, but right here is where it runs the actual hydraulic calculations, and it comes back from the calculations. Then it builds the output sheet. So that's all that's going on there. Here is the pump calculator. Jane friction factor, a velocity function, Reynolds number function. Initial guess uses pipeline only, no head losses and stuff like that. Then it takes the 3-point pump curve and builds a linear system based on that. Here's the actual pump curve function. So it fits a parabola through those pump curves. And then this is the pipeline function. And then finally, right here, it reads all the values from that form, makes an initial guess using the Jane equation model, and then from that initial guess, it actually implements Newton's method to get the updated guesses. So that seemingly simple interface has a lot going on. All this stuff could have been done by hand, and it would be fine, except that when you got to do hundreds of them, you probably want some automated tool. So let me quit that, exit the shell. So that's all that's going on. Let me get back to the beginning of the problem, and we're probably going to end early today. So presumably the worst failure mode would be the pipe breaking. That's the 24 liters per second. What we discovered is that that particular pump that we specified isn't, we need almost 3 of them in series to handle the worst case failure mode. Now the pipeline failings should be unlikely, but that's good to know. It means that we have to put some effort into the pipeline design, as well as some maintenance monitoring to detect failures before that happens. If, on the other hand, we accept that the most likely failure that we want to design and accommodate is the valve being left open at the schoolyard, so some kid leaves the valve open, one of those pumps, well, it's barely enough, would do the job. So if that's the only kind of failure we were worried about, we could specify the single pump, which is what was done, and use that to completely operate the system. The next step would be, let's suppose the pump fails, how long until the system fails? And that's a variation on the same kinds of thinking, but we would have to, essentially, if the pump fails, this side of the system is gone. It's not there. So the question becomes, how long can we supply water from just this tank? And we know we can because we have enough head even at the bottom of the tank. So we can run this tank dry. And so if we start with the 7 liters per second, we want to know how long it would take to drain the 6 meters from this tank. We need to know what the diameter of that tank is, and that's not provided. All we know is it's a large diameter tank. And that was all I wanted to accomplish today. Next time we're going to study pumps. Matthew, the answer to your question is, yeah, of course you can use the calculators on the server. That's the intent, actually. In the interim, what I think you should do is, I think you have another homework assignment coming up soon. I'll prepare some quizzes along these lines. You want to do them probably by hand once, and then check them with these online tools and convince yourself that you can operate the online tool effectively. And then it's simply on an exam matter be to run the online tool, screen capture it, add it to your document, upload it. That's about as in your face Dr. Cleveland as you can get. I mean, I have to accept it. Unless you put the wrong inputs in, that'll still be hard on my part because I'll have to find out what's wrong. The next lesson is, I'm going to look ahead a little bit. Pumping. Okay, so the next lesson is pumping. I think I'll, with your, do you all want me to stop now and pick up pumping on Thursday or get started with pumping? Can you give an overview of the homework due on September 17th? I certainly can. If I can find it. Okay, that's the 17th. Okay, so overview on, so this one is a layout of a hydraulic network, and you've already studied this map. In fact, exercise set 2, you built a map. You built a map based on these elevations that were on the black dots, and now someone has proposed a pipeline layout. So this is the network distribution system. The blue circles are nodes, and they have names associated with them, like N25. Let's see if I can zoom in a little. Let it render. Here we go. So this is node 25. That's node 20. That's node 21, node 16, 15, and so on. And then the blue pipes are shown here. The yellow polygons, so let's look at this yellow polygon right here where the cursor is, represent the lots that are assigned to each node. For instance, this is node 29, and it provides water to that house, that house, that house, that house, that house, and that house. So everything contained in its yellow area. It also provides water to the next node. So first, you want to go through some of the readings and guidance documents in lesson 2 and find the number of lots served by each node. That's pretty easy to do because that's from the map. And read what the definition of a service unit equivalent is and write that down for each node. Then estimate the average daily demand by node for the distribution system using the San Marcos, Texas design guidelines. Estimate the maximum daily demand by node for the distribution system using the San Marcos, Texas water system design guidelines. Estimate the maximum daily demand plus fire flow, again using the San Marcos, Texas water system design guidelines. So I think the San Marcos system has an explicit fire flow requirement. So it says, a certain number of gallons per minute per hydrant, every hydrant a certain number of feet. And then estimate the peak hourly demand by node for the distribution system using the San Marcos, Texas water system design guidelines. So when you've done all that, you're asked to put these into this table. And the importance of the table, not only for this lesson, because I'm going to look at the table and see if it's got numbers in it, is you're going to reuse this later on in the design project. You're actually going to put that information into a hydraulic model and evaluate the performance of this system. So that's all that exercise is asking. And then Marche, does that give you the overview that you're looking for? It's still work. I mean, this is not going to be a 10-minute job. It's not hard work, but it's a little tedious. But that's the nature of hydraulic modeling. So when you have this table completed, you can make your own Excel spreadsheet if you want with node ID and these different demands, and submit that. I can still read Excel tables, although that's ending. Okay, and then let's see, Raju, you want to look over exercise 2? You can certainly do that. Okay, so this exercise, you had this map of the same area, and you need to produce X, Y, and Z coordinates for each of the displayed elevations. The Z is given, and that's what the number is. And then you want to arrange them into a text file where each row of the file is a coordinate triple, and then you want to make a topographic map of it. That's the basis of this exercise. So one way to do it would be to grab the image. Let's see if Adobe Acrobat can handle this. Let's see. Save link as. Oh, it can't. Okay, so that can be opened in Acrobat. And we know that this distance is 1,100 feet. So my tool set, I should have measurement tools. Where are the measurement tools? Oh, it's not in the modern. Don't do that, computer. Well, Acrobat used to have measurement tools, so that's certainly an issue. Acrobat Pro. Okay, how do I get this to go away? No, don't do that. I said go away, not get bigger. Wild. All right, plan B. Let's see, don't save. Go back to the other desktop. Let me get the JPEG, because I do have a way to deal with that. Copy, save link. No, just come on, download. All right, so the old way of measuring things is a little harder. So there's this other tool here that is loading. And I'm going to measure the distances on the document, if it will ever load. Awful lot of work to get a stupid measuring tool. Hooray! Okay. Now we actually load the instance. Okay, here we go, cool. So I'm using a program called G3 Data. You can get it off the internet. There's a copy somewhere on my server. Ooh, that's very unusual. Stop. Okay, so should be network drive Z. So here's my map. And what I need to do is get this length in both the horizontal and the vertical direction. So I'm going to go ahead and roughly translate that distance. So from this main street to that main street with 1, 2, 3 cul-de-sacs intervening is about 1,100 feet. I'm going to make an assumption that from this black dot to that is roughly also 1,100 feet. If I had a ruler, I'd actually measure it. And I think about up here to this distance is about 1,100 feet. And I'm now getting the standard windows. You haven't paid us enough money last week. Go away. So let me go ahead and identify a point, set that as 0. $1,100. Zero. Take the input. 1,100. Let's see, remove points. Okay, so now I'm ready to start making measurements. And what this is going to do is keep track of the x and y coordinate of the cursor. So for example, if I go to that decimal point in the 70, right there, next one, next one, next one, keep track of what I'm doing. And you can't be willy-nilly, so you probably would be writing down by hand the order that you're making these dots in. And I'm going to skip over here to the end. And maybe we're out here, 26 and 26. Okay, so when you're ready for that, I can go ahead and export the data. Should have done it. Now let's go look at the data that we think we just exported. Oh, it's going to attempt to launch something that doesn't work. And now we have the x and y coordinates for those dots that we identified. Then we would go back, and by keeping track of the order that we did it, we could enter the associated z values from the map. So here we would put 70. Next one is also 70. So I was going from left to right, bottom to top. Next one is also going to be 70. Next one 68, and so on. Then we would save that file. Notice the file structure, X, Y, Z. This thing's ready to upload. We would then go to our toolkit, whatever you have. So if you have Surfer or you know how to do it in ArcGIS, you can do that. If you can't, we can go to a simple contour map. Now we just go ahead and grab somebody's. See, this is done on the 9th. There's someone practicing. That one's going to fail because it's got that blank spot in it. I like this one, so we'll go ahead and we'll use that. So let's suppose that represents all the contouring or all the XYZ data that we created. Paste it into the file name. Give it a challenge. I'm making numbers up. I'll keep my smoothing parameter at 0, so it's not even going to attempt any smoothing. And I like the inverse distance of 2. Let me submit it. Yeah, we've got to wait a while because it's thinking. And there's our contour map. Then, so it's got 70 here, and it's grading downward towards that stream. So that kind of looks right. Later on, we might manually enter artificial z values to make it render the stream correctly, but this is a good start. Here's those values at the different indicated locations. We can bump up the smoothing a bit. Little change, barely distinguishable. Bump it up some more. And what we're doing with the smoothing parameter is that because it messes with the arithmetic, we're kind of doing it to make the map look about how we perceive it should look. Let's go ahead and really challenge my computer a little bit. Okay, so at some point, I might stop like that because it's now starting to render that creek about right. And then there's the edge of the creek, and then we're moving up into the neighborhood. Then I would capture this picture. And from that, the next step would be to render it for an overlay. So rendering it with the overlay takes a few steps, and you'll have to use whatever graphics package you're comfortable with. What I'm going to first do is I'm going to clip on. I would want to clip out all that area. Okay, so let's suppose I've done that, and then I need to think it's markup. Yeah. Instant alpha. And then in preview, which is an Apple package, I can see how it did that. I can tell it to put all the stuff outside the crop as transparent. And you learn that by going to the Google Meister. Something like that. And then it tells you how to do it. And you work your way through, and when you're done, you can lay that map back on the original drawing, and then you have a contour map on top of the subdivision map. But even if you don't, you can still use the map that you made, so it has a whole description of how to do it, and there's going to be Windows equivalents. Okay, go back to the other window, please. There we go. So even if you don't, you can still use this map when you have the pipeline network to figure out what the node elevations are going to be. And that's part of the point of doing it. The other part of this map is going to be when we're doing the drainage engineering, we need to know where the streets are so we can figure out how to slope things for the drainage design. So that is the whole point of this map. And this is just one tool. You don't have to use this tool. By all means, if you have another contouring tool that you're comfortable with, use that. The effort of getting the XYZ data is the main effort involved. And what I've done here, you didn't necessarily have to use software. You could literally use an engineering scale and figure out how long 1100 feet is on the engineering scale, and then measure horizontal and vertical distances to each of these points and build the file that way. So quit that. See if I can get out of this Windows before it breaks something. Oh, I'm breaking a window. Hey, that's kind of funny. So that is exercise 2. I lost control again. To find the points on the map, I used a tool called Engage. And I think I have a copy, not Engage, G3 data is what the tool is called. Oh, it's not taking, oh, there we go. Let's see, old style archive. And Windows 32. I use this tool right here, this G3 data. So if you go there, you can, oh, it actually has an RTF version. So there's how to use the tool I used. I think the current version is a little bit higher than 1.3.3. And it shows you, in this case it's doing a curve, but it's the same, identically the same process. and then work through the program. If you're a Mac user and you don't have Catalina yet, there is I think there's a Macintosh version. Yeah, I have G3 data for a Mac right there, but if you have Catalina or Big Sur, it won't work. And the URL to get all this is just there in the chat box. See that one's, oh, that's still running. That's amazing. There's some other stuff here, but I don't think I have anything in the 64-bit. Yeah, and I don't have any Linux 64. PowerPC is empty. And this is completely outside the scope of this class. Oh, wow. Cool, full images. That's good to know. I forgot that I had that done. XY coordinates. So everything's there in those links if you want to use G3 data. I actually found G3 data like 25 years ago, and I'm surprised it doesn't get used as much as it could. So it's really handy. Some of the important things about it you'll need to figure out on your own, or I'll just tell you. It works pretty good with JPEG images. It can do a PDF image. It crashes a lot. So as you're getting data out of it, you want to save stuff a lot. Because restarts are pretty easy unless you've broken something. So with that, I am now at the end of our time. So I'm going to shut things down, and I will see you on Thursday. Let's check, I don't even know when this thing is due. It's due Wednesday, so there's still sufficient time to complete this exercise. So goodbye to everybody, and have a good afternoon. Go get something good to eat. What's the weather outside look like? Not too bad. I will see you next time. If I can figure out how to end the meeting. There we go.